We will start in chapter 6, the study of the entropy and the free energy. In the previous chapter, in chapter 5, the thermochemistry, we talked about the first thermodynamic data, which is delta H. And the meaning of delta H for a reaction: if delta H is negative, this reaction releases energy, so the reaction is exothermic. Or if delta H is positive, the reaction or the transformation absorb energy, so this reaction is endothermic. So in the previous chapter, we can know only if our reaction or our transformation is exothermic or endothermic. And we have several methods. We learned several methods to calculate delta H of a transformation. Now we pass to the inconvenience of the first law of thermodynamics. According to the first principle of thermodynamics, the energy cannot be created nor destroyed, and the energy can be converted only from one form to another. In the first principle of thermodynamics, we calculated the variation of the internal energy delta E, which is Q V is the heat released or absorbed at V constant, or we calculated delta H, which is QP, the heat released or absorbed at P constant. The most important inconvenience of the first law of thermodynamics that all transformations are possible. Example, we have a reaction from A to B that has a value delta H. In the first law of thermodynamics, we inverse the direction of the reaction and we put minus delta H. So we suppose by this way that the reaction from B to A is also possible, and the reaction from A to B is possible. So according to the first law of thermodynamics, all reactions are possible, or all transformations are possible, and this is not true. So for this reason, we pass to the second law of thermodynamics. In the first law, all transformations are possible. We pass to the second law to know which of the following process are or is possible or is impossible. Okay, this is the second law of thermodynamics. So on the second law, we explain why chemical processes tend to favor one direction. For example, the reaction from A to B is possible, the reaction from B to A is impossible. We have to explain what are the reasons for this theory. So we pass to the calculation of another thermodynamic data that we called delta S, the variation of the entropy or the entropy change. Spontaneous and non-spontaneous process. When reactants are brought together under special conditions of pressure, temperature, and concentration, or other conditions, sometimes we find that this reaction is possible or this reaction is impossible. So why the reaction occurs sometimes and did not occur, for example, at other conditions? The second law is a prediction whether or not a reaction will occur. And this knowledge is important in the research laboratory and in the preparation of the chemical. Suppose we want to prepare a new medicinal drug. We don't go directly to the lab in order to prepare this compound. First, we have to do thermodynamic analysis in order to know if the preparation of this compound or of this drug is possible. So we calculate, for example, delta S or other thermodynamic data of this reaction. From the thermodynamic data obtained, we can know that this reaction is impossible. What is the meaning? This reaction is impossible, so it's not necessary to go to the lab in order to prepare it, because by theory, we could not prepare the substance. So the answer is in the second law of thermodynamics. Spontaneous reaction is a reaction that occurs under the given conditions without external effect. Okay? Non-spontaneous reaction, that means in the given conditions, this reaction could not occur. It can be spontaneous if you change the conditions. I will give example. In grade 12, sometimes we say that this reaction need a catalyst. Okay, need a catalyst. The reaction from A to B is impossible. So this reaction in the given condition is non-spontaneous. If you put external effect, if you put catalyst, sometimes this reaction will occur. So you transform a non-spontaneous reaction, you did an external effect to make it spontaneous. So spontaneous reaction occurs automatically without external effect in the given conditions. Non-spontaneous reaction in the given conditions, this reaction did not occur or this reaction is impossible. Examples: a waterfall runs downhill but never up. If you have, for example, water, the water fall down. I take the example of water. Water fall down without external effect, but never up. You need a pump in order to make the transformation in the opposite direction. If you take a piece of sugar and you dissolve this piece in hot water, what are the conditions? The conditions is hot water, so the temperature is high. If you put a piece of sugar in hot water, the dissolution of the sugar is spontaneous. It will dissolve directly at the given conditions. But take, for example, a piece of sugar in different conditions in cold water. This dissolution, the piece of sugar would not dissolve. So the piece of sugar, this transformation is non-spontaneous. Look, for the same piece of sugar in hot water, the dissolution is spontaneous. The dissolution of a piece of sugar in other condition in cold water is non-spontaneous. The reaction between sodium react with water to give sodium hydroxide and hydrogen gas. This reaction is spontaneous and highly exothermic. Take sodium hydroxide and hydrogen. This reaction would not form Na and H2O. So the reaction between Na and H2O is spontaneous. The reaction in the opposite direction between NaOH and hydrogen is non-spontaneous. How to predict if a transformation is spontaneous or not? If we want to study the kinetic of a reaction, this is to note, if we want to study the kinetic of a reaction, the important condition that this reaction occurs first. If the reaction is spontaneous, then we can study the kinetic. of this reaction. So now, how to predict if a process is spontaneous or not? Can we use the first law of thermodynamics? Can we use the value of delta H or the sign of delta H in order to know if the transformation is spontaneous or not? I will consider two examples. The first is the combustion of methane, CH4 gas plus O2 gas gives CO2 gas and H2O. The reaction of combustion is always exothermic and delta H equal minus 890.4. This reaction is spontaneous and the reaction is exothermic. Consider another reaction, another dissolution, which is the dissolution of ammonium nitrate in water. Ammonium nitrate in heated decompose spontaneously to NH4 plus and NO3 minus, and this reaction is endothermic and the reaction is spontaneous. The first is exothermic, the second is endothermic, and the two transformations are spontaneous, so we could not relate, we could not predict the spontaneity of a reaction based on the thermodynamic data delta H exothermic or endothermic. So we cannot decide whether or not a chemical reaction will occur spontaneously on the basis of the energy change in the system. So delta H of the reaction is not an indication about the spontaneity of the reaction. Delta H of the reaction or delta H of the transformation is an indication about the nature of this reaction, exothermic or endothermic. Later, we will see to predict the spontaneity of a reaction, we have to pass first by the calculation of delta H. So the energy change calculation will help in the prediction, but this energy is not the indication about the spontaneity of the reaction. What are the factors that affect the spontaneity of a reaction? In the next part, in part 2 of this chapter, we will pass to the calculation of new thermodynamic data, which is delta G. And the sign of delta G is the key of the spontaneity. If delta G is negative, we will see that the reaction is spontaneous, or if delta G is positive, the reaction is non-spontaneous. So delta G is the key and will be studied later in details in part 2. To calculate delta H, we have to calculate delta G, we have to calculate delta H first, then we have to calculate delta S. So the factors that affect the spontaneity, in general, the reactions are spontaneous in the direction of lower chemical potential energy, so the system tends to have lower energy. If our transformation passes from a system of high energy, of high potential energy, to a system of lower potential energy, we can predict directly that this transformation is spontaneous. Two factors determine the thermodynamic condition of the spontaneity. First, the enthalpy change that was studied in details in chapter 5, and now we have to define a new thermodynamic data, which is the entropy change. So to know if our transformation is spontaneous, we have to calculate first the enthalpy change delta H by the 4 methods studied previously. The second, we have to calculate delta S, which is the entropy change. From the combination of delta H and delta S, we can have conclusions, and from this conclusion, which is delta G, we can know if our transformation is spontaneous or not. So now we have to define in the next slides what is the meaning of the entropy. The enthalpy change delta H is the difference between the internal energy and the work, and this formula or this relation was studied previously. So now, what is the entropy change delta S? The entropy change delta S of a transformation is an indication about the randomness of the reactants compared to the product. What is the meaning of this statement? Consider a transformation or a chemical reaction where we pass from reactants to products. The reactants has a certain organization, has a certain order. They are organized in a way, and the products are organized in different way. So the difference in the organization, or the difference in the randomness, or the difference in order, is the entropy change delta S. Definition of the entropy. Entropy S is a thermodynamic function that indicates the order or the disorder or the randomness of the substance. This is an indication about the way the substance is organized or non-organized. Consider ourselves. I can say I am organized in my life. Another student say I am not organized in my life. These two statements are related to the entropy of the person. I have a value of entropy S, and my colleague has another value of entropy S. According to this value, or we can compare the S of student 1 and S of student 2, we can know which of the two students is more organized, is more ordered. More organized means more ordered or less disordered. So the entropy is identity of a substance. Every substance at a given temperature and in a specific phase has a well-defined entropy. So the entropy is identity of the substance. Till now, what are the identities of the substance? Any substance has a value, has identity Cp, has identity Cv, has delta H of formation, and now we add a new identity. Any substance has a value of entropy S. When the entropy increases, that means the disorder increase. If I have two substances, the first has entropy S1, the second has entropy S2. If the entropy S1 is greater than the entropy S2, that means the substance 1 is more disordered or is less ordered or is less organized. So disorder means non-organized, order means organized. So when the entropy of a substance increases, the disorder increases. In a transformation, we have difference between the entropy of the initial state and the final state. Therefore, for the transformation, we calculate the entropy change delta S. S is for substance, delta S is for transformation. In the first law, delta H formation is for substance, and delta H of the reaction is for the reaction or for the transformation. Example of entropy. First, consider the physical transformation process that lead to increase in entropy of the system. Suppose we have a solid that is transformed to a liquid, so this is a melting. Look first to the solid. The particles are very organized. In the liquid, the particles are less organized. So S of the liquid is greater than S of the solid, since the liquid is less ordered than the solid, or I can say the liquid is more disordered than the solid. So when we have melting from solid to liquid, S of the liquid is greater than S of the solid, so delta S for this transformation is positive. Suppose we have liquid to vapor. The particles of the vapor are less organized or are less ordered, so S of the gas is greater than S of the liquid, and delta S of this transformation, which is the vaporization, delta S is positive. In transformation C, we have dissolution. We dissolve a solute in a solvent to obtain a solution. Previously, before the dissolution, the particles of the solute and that of the solvents are well organized. After, we have particles of solute between the particles of the solvent, so the organization decrease, the order decrease, or the disorder decrease. So S of the solution is greater than S of the state when you have solute plus solvent, so delta S of the dissolution is positive, of the mixing is positive. In part, in transformation D, we have a system at T1 that is heated at T2 without a change of state. So when we heat a system, we absorb energy, and the particles will absorb energy, so the motion of this particle is greater than the initial system. So the system at temperature T2 is less ordered than the system at T1, or I can say the system at temperature T2 is more disordered than the system at T1. So S at T2 greater than T1 is greater than S of the system at T1, and delta S of this transformation is positive. So in the physical transformation, you can deduce delta S of the transformation positive when you pass from solid to liquid or from liquid to gas. You can say directly delta S of the dissolution or delta S of the mixing is positive. If you have a transformation where you increase the temperature without doing any calculations, you can say that delta S of this transformation is positive. The factor 4, when we pass, for example, from helium gas to neon to argon, krypton, xenon, we observe that all these are gases. So how to compare their entropies? Since these elements are gases, so the gas with the larger molar mass has the higher entropy. In other words, if you compare two substances at the same state, gas and gas, the element with the higher molar mass is more disordered or is less ordered. That means S is greater. If you compare, for example, two solids, you compare the entropy. The solid with higher molar mass has higher entropy. Now we pass to the chemical transformation. How to predict the delta S of a chemical transformation, delta S positive or negative. A chemical reaction, in the chemical reaction, we pass from reactants to products. First, if the reaction forms gas, that means we pass to a state that is less ordered or that is more disordered. So the formation of a gas in a reaction means delta S is positive. Suppose our reaction forms solid. That means when we pass from reactant to product, we pass to a state where we organize our particles. So in this case, delta S will be negative.